Okay, so today's goal would be to actually see how the various puzzles in black holes are resolved in string theory, which means we have to understand how black holes are made in string theory. So I know that most of you have not worked with string theory, and the way we are going to do it is that you will not actually need to know anything about string theory. Whatever you need to know, we are going to develop as we go along. Okay, so string theory is actually very simple if you just want to understand how to use it to understand black holes, and so that is the goal. We will just move in very simple steps and derive whatever we want to. So today we have two goals. The first is to derive the formula for the entropy of a black hole. This is a very famous formula by Strominger-Vafa, who actually showed that in string theory the entropy of the black hole matches the value which is given by this area upon 4 kind of formula that Bekenstein had found. So we will do all the calculations and get all the way down to the answer with the last factor of 2 and pi, and it is easy to understand this without really knowing any complications of string theory. It just needs basic properties of strings, and we will learn the properties and then we will use them. Okay. Then the second goal would be to see, we will see that counts the entropy and tells us something about the entropy of a black hole, but we will also see it doesn't solve the information puzzle. If the black hole still has some area but it has a smooth horizon with that area, then you will still have the entangled pairs and so on. So we want to see what we had seen in the first lecture, that black holes are actually fuzzballs. They're actually quantum objects which are as big as the horizon, and really black holes don't have the traditional horizon that people do. So we will actually see the whole construction of fuzzballs. Again, from first principles, you will not need to know anything deep about string theory, but you will see how the exact formula for these actual black hole states come out. So between these two, then we can understand how all the issues of black holes are resolved. We will understand their entropy, and we will understand how they resolve the information puzzle. Okay, so that's the goal for today. But because I know that you guys don't actually work with string theory by and large, so we should go particularly slowly. Like even yesterday we were like stopping for questions whenever we need to, and today we should do that even more. So all the time we should just pause on every slide and just slowly keep looking at what is there till we understand the picture. It's all just pictures, and that's all we need. So let us first summarize what we have learned so far. So we have seen that if we have the vacuum around the horizon, it creates these entangled pairs, and this is some low energy process. We saw it was just 2 harmonic oscillators which are coupled, and then they become uncoupled. We don't need any quantum gravity for that, and then that leads to a problem. What is the problem? Because when the black hole disappears, there are 2 possibilities. If the black hole completely disappears, then whatever you are left with, it is entangled with something, but that something is no longer there, and so this thing can't be given any particular state. You remember the story here, if 2 electrons are entangled, spin up, down, minus, down, up, that's okay. But if 1 electron disappears from the universe, the other one doesn't have any state, because it was up if the other guy was down, it was down if the other guy is up. If the other guy is not there, it doesn't have any quantum state. So this is a problem. It violates quantum theory. And then to get away from that, people had said maybe the evaporation stops when the black hole reduces down to becoming Planck size, because then quantum gravity effects may come and somehow stop the further evaporation. But that's very complicated, because then all these things are entangled with all these partners, and we had talked about the fact that something very small, if it needs to have a high amount of entanglement, then it will need to have a lot of internal states, and if you have something very small, how can so many things fit in such a small volume? So none of the solutions was working very well, and this was the information puzzle. So then people had thought that perhaps small corrections can solve the problem. That is, even though this particle is entangled with this particle in Hawking's leading order calculation, there could be small correlations between this particle and any of the other particles. If these are small, you might ask, why do you want to worry about it? But then the point was there are so many of them, because there are so many particles here. So from this particle I could draw the dashed line to so many other particles, and so maybe that will help you to get the entanglement from growing, and if you take into account some leading corrections, maybe it will make it come down, and then there will be no problem. But then we had seen that there is a small correction theorem. If you try to write this down explicitly, if the emission was described by this in Hawking leading order effects, the last time we tried to make a model of putting small corrections, that if at the first step you had 0 B1 0 C1, and then also you could have 1 on 1 or 0 and 0. If you have 0 and 0, you have a little bit more of 0 0 and little less of 1 1 at the second step, B2, C2, or and you could change it differently for the 1, 1. So you could correlate them all carefully, but then you have to write down these steps and try to take a look. And it does seem there are a lot of correction terms after n steps, the 2 to the n correction terms. So at first you might think these small corrections might help you, but a small correction theorem actually told you, no. If you have the epsilon is small, the corrections are small, the fact that there are many, many pairs n, that doesn't help you. If it is small, it will actually always remain small, the corrections, and so you can't get out of the puzzle in any small way. Okay, so we had seen that in a piece of coal is different, because first the entanglement grows, but then when the other atom comes out, the entanglement comes down, but black holes don't behave this way. So we still have the problem, but in the process of this discussion, we realized the Hawking's argument is now a completely rigorous theorem, which we have to worry about. If the horizon remains like a vacuum region, now to leading order, that's very important. Any small quantum gravity corrections you can put in if you like, but they will make no effect to the argument. If the horizon behaves like this room to leading order for low energy physics, you're already finished, you can't save quantum mechanics. Now that's a really serious thing, because now you have to somehow change the horizon of a black hole, and a black hole can be very big, 3 kilometers or 10 to the 8 kilometers, depending on what kind of black hole you're looking at. And then you still have to change the horizon by order 1, the physics around the horizon to order 1, and that's certainly a tall order, because it means quantum gravity is going to do something very serious. I just wrote down here the actual Page theorem, because somebody was asking about it last time. If you have two systems with m states here and n states here, if m is smaller than n, then the entanglement between them in a generic state is given by log of the dimension of the smaller system. So that was common sense, was always known. Page's contribution was to compute the next correction, and that is m over 2n. You don't need for anything in this talk, but people often call this the Page curve, but the Page only computed how this thing sort of rounds off at the top. So this particular shape here is given by m over 2n, in case anybody was interested. Okay, so this is just where we were last time. All we know right now is that from the Hawking argument, which has now been made completely precise by the small correction theorem, we need to change the structure of the black hole completely. Okay, so how will this happen? And the reason it looks very difficult to do right now is that string theory just changes physics. You would think at the Planck scale, it's a theory of quantum gravity. So if you change something right near the singularity or something, it won't change the horizon. And if you don't change the horizon, if you can make only maybe perhaps small corrections to the horizon, it won't help you. So we can see the problem that at first it's not clear at all how string theory will help us. And so as we go through this, we should try to see what is it that string theory does which can possibly help us. Okay. So as I said, the question is, how can strings help to solve our puzzle? Hawking's paradox is so strong because it does not use any details of quantum gravity. We just use physics around here. And so if the only scale for quantum gravity is that if you collide two gravitons and you scatter them until you get to Planck scale, you don't expect any new physics, because the only length scale you can make from C, H bar and G is Planck scale. So nothing changes up to Planck scale. And so it doesn't seem that string theory can do anything. Even if you have strings, they also fall into the black hole. Particles fall into the black hole. Everything goes in and leaves back a smooth horizon. So how on earth can string theory ever help you solve the puzzle? Okay. So now let's begin our understanding of string theory. And so here you should keep stopping me and asking lots of questions, because we are learning all the string theory that we need in the process of deriving what we want to do. So this is where we really start. Let's look at the story. So the graviton is always there in any theory of quantum gravity. So what is a graviton? Just like you have gravitational waves, then if you look at a single quantum of those waves, that will be called the graviton. Just like you have electromagnetic waves, and the single quantum of that is called the photon. So whenever you have any kind of classical wave, you can keep reducing the amplitude till you come to the smallest amplitude excitation, and that will be called the photon, or in this case the graviton. So string theory, of course, has the graviton as a particle. So what else is there in string theory? Then you also have the string. It's called NS1 for certain technical reasons. We don't have to get into that, but at least the 1 stands for the fact it's a one-dimensional object. A string is like that. The only thing you need to know about a string is that it's like a rubber band whose relaxed length is 0. If you let it go, it will come to 0 length. But if you stretch it, it costs energy, and the energy is linear in the stretching. So the more, just like a spring, the energy is proportional to the stretching. So if you stretch it to some length L, then the answer is proportional to L. Okay, so that's all that we need to know. So that's a string. It's normally a closed loop, so I draw it like a closed loop called a closed string. But then you also have sheets of other dimensions. For example, you can have a 5-dimensional sheet. It's called the NS5 brane. So it will just be a sheet, and again, if you let it by itself, it will shrink to 0 size under its own tension like a rubber sheet. But if you stretch it, it will cost you some amount of energy per unit area. The area is now a 5-dimensional area, so you should call it maybe a 5-dimensional volume, but it's proportional to the volume. That's all. So everything is very simple in string theory. For example, in particle physics, you have particles of different masses, but in string theory, it's not like that. You just have these fundamental objects. If you leave them relaxed, they just go to zero mass, and they just become like the graviton. But if you stretch them, then the energy is proportional to the volume of stretching. Okay. So then you have other things which are 3-dimensional sheets, 7-dimensional sheets, 9-dimensional sheets, all them. Some of them are called D branes. They have a D in them. Some are called NS branes. It will not matter for our purposes, but have many of you heard about the word D brane? Okay, just a kind of particle in string theory. None of it will be relevant to us. The only thing relevant is that these are objects which are like rubber sheets, and if you stretch them, they cost you that much more energy. There's also something called a Kaluza-Klein monopole. This you might have heard about in gravity. It's like a topological knot in space-time. Okay. Again, you don't have to know about it, but it's one of the objects you can make in a gravity theory. So stretching means, suppose you take a string and you have to stretch it, like suppose you can, let's say, wrap it around a circle. So suppose in space-time you can have a circle, right? A compact circle. So you can take a string and imagine it to go around the circle and join back. So you can ask, what's the energy of the string? The energy of the string will be proportional to the length multiplied by the mass per unit length. So every string has something called a mass per unit length. It's called the string tension. It has a definite number in string theory, and that number multiplied by the length of the circle will tell you the mass. So if somebody gave you a circle of twice the radius, the string wrapped on that has twice the mass. So it is really that simple. Okay. Yeah. So more questions like this. You should become very comfortable with string theory, because this is all there is to it. The energy just depends on how much you stretch it. So then the interesting thing is that in the theory you have something called dualities. They're called S dualities and T dualities. You don't have to worry about the name. But duality is a kind of symmetry. And under symmetry, for example, you have symmetries which can rotate the 3 colors of quarks into each other. Like you have SU3 symmetry. So a red quark is as good as a green quark or as good as some other quarks. So you can rotate them among each other. You also have like flavor symmetries where things that behave identically, but they can be of different flavors. So this is more like a bit of a flavor symmetry. If you make one of these dualities, it can interchange the graviton with a string, or the string with a 5-brane, or 5-brane with a Kaluza-Klein monopole. All these guys are connected to each other by symmetry. So it's like the neutron and proton. They form a doublet, and by symmetry, you can rotate one to the other. It's called isospin symmetry. So they are all sort of like this, connected by some symmetry groups, and those are called S and T dualities. Somebody had a question. Yes?
So does this string actually closed? It has a closed structure?
Say louder, please.
The string is closed.
Closed.
Yeah.
Okay, so you can also have theories which have open strings, but there is a problem because you have to know what to do with the ends of the open string. Okay, like what happens at the end. So the simplest theory is one where the string is closed, and you don't have to worry about the ends. Okay, if you do take an open string which does have ends, then you have to ask, the end can only do certain special things. You have to like tie it down to something. So for example, you can have an open string, and then you can attach one end to one of these D branes. You can attach the end of that string to one of these kinds of sheets. Okay, so there are definite rules. Like if I gave you a string, it will just shrink away unless I tie it to something, right? So I can like tie it to this window, for example, and I can tie it to this window. So if I have one of these branes, let's say over here, and another of these branes, let's say over here, I can take an open string and I can start it here and I can end it there. Okay, so absolutely, everything is completely simple, and whatever you're thinking intuitively about strings is going to be true. Okay, yeah, another question.
As a follow-up to the question, the D-branes also have to be open, or they can be closed as well? I mean, they have to...
Okay, so the same story. The simplest D branes will be closed. Okay. And closing, there are 2 ways to close it. You can just make like a balloon out of it like this, but then it's going to shrink, right? If you just take a balloon, it has tension, it's going to shrink. If you wrap it around something, like if there's a torus, like if the room was doubly periodic on both sides, then you can wrap a 2-dimensional sheet on it. That's the most common way to use the D brane. But yes, they can also be opened. So for example, you can take a D3 brane, and then you can have a D5 brane here and a D5 brane here, and the D3 brane can stretch from here to here. Like the end has to be on something. You can't end it in the middle of nowhere. So it has to attach to something, otherwise it will just shrink away. So there are rules for what it can attach to. And so for example, a D3 brane can attach in a perpendicular way to a D5 brane. Okay. So there are definite rules, yeah.
If any of this, if a part of any of this extended object, let's say string NS prime or D prime, is inside the horizon and the rest of the part is outside,
yes.
Is it under the effect of the black hole?
Yes, so you can do that. One part is inside, then the string goes and is outside. It has all the effect of the black hole. The gravity is acting on the whole thing. So the gravity will try to pull the string in. Whatever you intuitively imagine, if you just took a normal elastic band, like a rubber band you buy in the market, and you throw one end into the black hole, whatever that one does, this guy will do. Nothing new or special. Everything is just elastic bands. Yeah.
So why are the braids all odd dimensional?
Okay, so that's a very interesting. When you get into the details of string theory, you find that the fact that you only have certain dimensions, that has to do with supersymmetry. Okay, so there are two kinds of string theories. There's something called type 2A string theory and something called type 2B string theory. In type 2B string theory, you get all the odd dimensional branes. In type 2A string theory, you get all the even dimensional branes. But that has something to do with the structure of the fermions in the theory, which chirality they have, and which I'm not going to worry about here on the board. So I'm just working in type 2B theory. I wrote it here, and that has the odd dimensional branes. So if you don't put the even dimensional branes in this type 2B theory, the fermions will not behave themselves. They have some problem. Supersymmetry will not allow that. So string theory is very, very rigid. It's very important that the mass per unit length of this string or the mass per unit volume of these guys, they are not arbitrary parameters. They're just completely fixed by these duality relations. So all these numbers are known. And so how strongly things interact is all completely fixed. And what kind of branes you can have and what's their mass per unit area is all completely fixed. So string theory is a completely rigid structure. There's absolutely no change possible anywhere. So if you try to make a black hole with this and you don't get the correct entropy, the whole thing is gone. So that's why this entropy calculation is so correct, so important, because if you get the entropy correct, you verified something great, that it has the right property to be a theory of quantum gravity. But also if it doesn't work, there's nothing to fine tune. It's not like particle physics, you can change the mass of the neutrino or change the, some Cabibbo angle somewhere and try to fit things. There's nothing to fit. Either the whole thing gives you the correct entropy or it fails. So that's why the calculation is so, there was a hand up somewhere here. Yes?
Can a photon also be an elementary object in string theory or any quanta of some massless field?
So there is nothing beyond this. If you want a photon, you have to get it out of here. And the way people get it out of here is that if you have heard about dimensional reduction, we said there are 3 plus 1 dimensions around us, total dimension is 10. So we have to make 6 circles compact. The graviton has 2 indices, g, mu, nu. If one of the indices points in the compact direction, we don't see it. Then the other index, nu, is in the non-compact direction, it looks like a photon. So every time we get a photon, this is an old story, even before string theory, people have gotten photons out of what's called dimensional reduction. You have an extra dimension, that's an extra circle. Now there will also be a component, sometimes the direction is called W, X, Y, Z, and that's W. Then the component of the metric, which is dWx, GWy, GWz, will be AX, AY, AZ, the vector potential. So you are going to get the photons out of this. It's very important that you have to get everything else out of this. If you want an electron, it's also going to have to come out of all this. The only thing you have to play with is what you do with the 6 compact dimensions, different ways of compactifying it, and then different ways of dealing with these things with those directions. That's all that you have. If you can't get the standard model out of it, you're in trouble. So people have tried to get a standard model. It sort of works, doesn't work very naturally. It's been a puzzle, but you can't go outside this. You can't add a photon to this. It's not consistent. Okay, any more questions on this? This is very good. This is the basic string theory, so we should focus on this.
Are these the only objects which we can consider in string theory?
Yes. You can't add anything and you can't delete anything. If you remove one of these, for example, or if you add one more object, some fancy object over here, the theory will become inconsistent immediately. Zero choices. Dilaton, graviton, yeah, I sort of put it in the graviton multiplet, yeah. So I should mention that along with the graviton, because of supersymmetry, these actually form what are called multiplets. So along with the graviton, there are its partners, there are some other gauge fields in the theory and so on, and they together make a full supersymmetry multiplet. So there will be a graviton, its supersymmetric partner, the gravitino, then in the same multiplet you'll find some gauge fields, and the multiplet keeps going on, and in that multiplet will also be the dilaton somewhere. Right? So there's a 256 dimensional multiplet here, which is all coming from supersymmetry, and I have not written that, but that actually will show up sometime later. Even this string, you can take the string, you can find its super partner. For a boson, there's a fermion, and the string itself, there'll be 256 states of it because you can find supersymmetric partners. So normally in supersymmetry, you might be used to one boson pairing with one fermion, You might have heard that it's supersymmetry, but when you have such high dimensions, the supersymmetric multiplet keeps going on. You have like the multiplet much longer, and it has 256 elements in it. It is implied because if you have no supersymmetry, nobody has been able to make a stable vacuum. If you take the bosonic string without supersymmetry, its vacuum is unstable. It has a negative mass squared state called the tachyon, and the whole thing just collapses. So it's better to start with supersymmetry. Okay, so now let's look at some properties of the theory. This was the first property, that we know the elementary objects of the theory. Then, as just mentioning, the string coupling, we call it G. The coupling tells you how strong these guys interact with each other. Okay, so that is a scalar field called phi. So normally you can ask how strong is the coupling in a theory. Like in electromagnetism, it's alpha square, alpha which is 1 over 137. It's a fixed number, we can't change it, but then you can ask where does it come from, and we don't have an answer to that, right? We don't know where the 1 over 137 comes from for this number alpha, which is E square over H bar C, right? We don't know where it comes from. But in string theory, the coupling is actually one of the scalar fields of the theory. This dilaton field, it's part of the supergravity multiplet, I said. And this scalar field, it can be big here, it can be small somewhere else. Just a field, like a scalar field. But e to the phi, the scalar field, that is the strength of the coupling. So if you have a string here, another string here, and you want to know if they interact with each other or don't, the interaction is also very simple. If there are two strings are coming, they can break and they can join in the other way. Like one string comes here, then this piece can join with the piece of this string, and this piece can join with the piece of this string. Everything you think intuitively is exactly all that is. Okay? But what is the probability of joining? What is the strength of the interaction? That is governed by this thing called a string coupling. So that's very important. The coupling is not fixed. If it was a fixed number like 1 over 137, then you can't imagine changing it, right? But because it's like it's a scalar field, right? I can first take the value of scalar field to be small, then I can gradually increase it in this room till it becomes big. I can compare something at weak coupling to something at strong coupling. We'll actually be using that trick today. It's easier always to compute something at weak coupling, and then you gradually increase the coupling till you get to strong coupling. But because it's a unified theory, the coupling includes coupling between all particles, but also the gravity coupling. So if I make this coupling small, even gravity is switched off. So everything is very easy. If I make the coupling big, now gravity is strong, and that's when I'll get a black hole. So that's very interesting, because if black holes are confusing, we can take a black hole which comes when gravity is strong. We can imagine taking this G parameter and making it smaller and smaller till the gravity is gone. Then the black hole will just become a bunch of particles. Particles means the things we had on the previous slide, strings, brains, and so on. But they're pretty much free particles because all the couplings are gone. So if you can understand these free particles, and then you can increase the coupling back, and on the other side you have the black hole, that's a wonderful tool to understand what's happening in black holes, because this coupling is actually completely changeable. So all these are intrinsic properties of string theory, but they help us a lot in understanding black holes. We already mentioned that string theory lives in 9 plus 1 dimensions. I guess you guys already sort of knew that. So some of the dimensions have to be compactified to get a black hole, let's say 3 plus 1 dimension, and 6 of them have to be compact circles. So I'll draw the picture like this. This is a non-compact direction like X, Y, Z. But this is the compact directions. You can call them W1, W2 up to W6. Is that okay with everybody? Yeah. Then we already said this theory is unique. The set of elementary objects, the tension means the mass per unit length, and the interactions are all fixed. We already said that. There's no room anywhere. So either the whole thing works to give black hole entropy, or the whole thing falls flat on its face and we have to go home. Okay. So now if you want to make a black hole, you have to use the objects in the theory, because you can't add anything from outside. Like normally in particle physics, if you're studying something, you say, let's take a scalar field, and then let's take a fermion field, and let's write this Lagrangian as a toy thing. But you can't do that in string theory. Whatever you have is what you have. We already said that, right? Okay. So you have to make a black hole using these objects. So what are we going to do? Suppose you take gravitons, then you try to put them in one place to make like a heavy object like a black hole, and you find you can't do that because they are massless particles. They'll just run away. Okay, so you don't make a black hole that way. But let's see how we can actually make a lot of mass to stay in one place to make a black hole. You can take a string and you can wrap it around the compact image. So the mass of this we know is the mass per unit length of the string, which is a fixed parameter, and multiplied by the length of the circle. That's the mass of this guy. Okay, so now you can see I've basically put some mass in one place, and more complicated objects like this, that's all I can do to make black holes. To get a large mass, we should take many strings. So you can see that if you can't resolve the compact direction, if you can't see what the size of that circle is, like normally we can't see the compact direction because there are a few Planck lengths in size, then they will just look like little mass points to us, and that's fine. We get little mass points. But that's not what we want, because this looks like lots of different tiny black holes. We want one big black hole, and to get one big black hole, we should make a bound state of these guys. So what is a bound state of many strings? So what's the bound state? For example, the hydrogen atom, you have the proton, you have the electron, there are two objects. The bound state is the wave functions you find in your undergraduate quantum mechanics book, right? So it's usually pretty hard to compute the properties of bound states. For example, if I ask you the energy of the lowest bound state of the hydrogen atom, it's a pretty complicated formula. Right? The value is minus 13.6 eV, but we have to actually calculate that in terms of all the e square over it has e to the power 4 in it and all that. So it's a pretty complicated formula. But in string theory, everything is very easy. String theory is much easier than everything else. So the bound state of what's the bound state of many strings? You simply take your string, you wrap it around the circle, and then if you want a bound state of two strings, you wrap it once more, and then you glue it back to itself. So just an elastic band, which is wrapped twice on the circle. So what's the energy of two strings bound to each other? There's no binding energy. It's the mass of one string plus the mass of another string. It's just the mass of two separate strings. Okay? So there's no binding energy. The mass of quantity A plus quantity B, the bound state has mass MA plus MB. Okay? So it's as simple as this, and that's all the bound state of two strings are. Or you can bind n strings, and so here's my cartoon of binding n strings together, and that makes one big mass. Somebody had a hand up there? Yes.
Can we change the width in the compact directions? Like as you said that the mass of the particle will depend on the...
This width, this size?
Yeah.
Yes.
The compact direction, can we have different widths so that the...
Yes, you can. So the width of the compact direction is not fixed by anything, and different widths of the compact direction, the length of the circle you mean, right? Different size of this circle are what are called different compactifications. So string theory doesn't tell you what compactification to choose, right? So sometimes there are many discrete choices. In this case, there is a continuous choice. You can make it any number. And right now, yes, I can make it any number. And that's very important, because in the end, if I get black hole entropy to work, the formula it should give me A by 4 should work for all sizes of the circle. So the mass of this guy obviously depends on the circle, because we said it's mass per unit length times the length of the string. So the length of the circle will keep coming in the formula all through. But in the end, it's very important, it has to cancel beautifully. When I match it to A by 4, it has to cancel beautifully. And it will all cancel beautifully. That's the part of what we are going to see. It works out very nicely. The one other thing, so when you put all this together, it looks like one big blob of some mass m, so I wrote the m. I think we mentioned this before in some other talk, that these things also have a charge. We call it winding charge, because the string oriented this way is opposite string oriented this way. If I wrap the string this way, it has positive charge. If I wrap this way, it has negative charge. Okay, so it has some charge also. And maybe we said this also in the first talk, that all basic objects in string theory are what are called supersymmetric. The mass is exactly equal to the charge. What is the meaning of mass equal to the charge? It means you take two identical copies of this, maybe one string here and one string here. Suppose you wrap one string over here, let's take this one and this one. Then they will attract each other with gravity, because they all have mass. They both have charge. Suppose I wrap them in the same direction, so they both have the same charge. They will repel, but the attraction is equal to the repulsion, and so they will stay where they are. That's the meaning of mass equal to charge. So all the elementary objects in string theory are like this. If you take a three-dimensional sheet here, and another three-dimensional sheet here, they will attract by gravity, repel by their electromagnetic force, and they will exactly stay where they are. Okay. If one is a string going this way, and one is a string going the other way, can you tell me what will happen? The mass is not zero, because this one is elastic band, its mass is equal to something, and this guy has the same mass. So the mass adds up. What about the attraction between them? The gravity is attractive, and the electromagnetic force is also attractive. So now they'll just come and crash into each other. But if they go in the same direction, then the repulsion of electromagnetism will balance the gravitational attraction, and that's the meaning of this statement, m is equal to q. Okay. Well, so after they come and they collide with each other, that's a complicated dynamic which you have to solve. Because now there's extra energy, right? So and there's no net winding number. There's a winding number +1, there's a winding number -1. So it can just become gravitons and they'll run away. Okay, so now the question is, if you do this and you put all this mass here, does it actually create a black hole for you? We are trying so hard to make a black hole. We are trying to put all the objects together to make a black hole. Have we succeeded? Okay, let's see if we have succeeded. So we have done this, and if you don't resolve the compact direction, you can't see this, it looks like a point blob. We said that the number of times I wrapped it, we'll call it a number n1. n1 is the number of times I wrap this one-dimensional objects. I'm just trying to set up notation for later on. It's a one-dimensional object, the string. Like the three-dimensional object, I can call it n3, the number of those, and I can call it n5. But there's only one object whose number is n1, one-dimensional lines, and I've taken n1 of them. N1 could be 10, 100, or whatever. and looks like a blob. At weak coupling, this is all it is. It's just a free string, so I understand the picture completely. So the question is, if I increase the gravitational coupling now, does it create a black hole around it with mass m? It turns out it doesn't really do that. It turns out that when you work with this and you try to find the metric it creates, the geometry it creates, far away the geometry will be flat space, because when you go away from everything, you get Minkowski space. That's not surprising. As you come closer, space begins to curve. That's also true even if you have a star, space begins to curve. But it doesn't actually end up creating a horizon. It sort of curves like this, and at some point, you just get like a little singularity, but no horizon. Okay? So it's funny, you don't get a horizon, or if you like, the area of the horizon is 0. So for this, you have to actually go and solve the metric and see what you get. So the reason you didn't get a horizon is because of the charge. Normally, if you just have a lot of mass in one place, that gives you the black hole of mass m. What else is a black hole? A black hole is the geometry you get for a point mass m. It gives you the Schwarzschild geometry of mass m. But if the guy also has some charge, you have to be careful. You have to ask what the charge is doing in that particular theory. And this particular theory, if you take the charge which is given by a string winding, it actually doesn't create a horizon area. It creates this kind of singular geometry with 0 area. Okay, let's ask if this is good or bad. Actually, this is good. Why is it good? If you ask how many states there are here, if you just wrap the string and you leave it, doesn't matter how big n1 is. Suppose n1 is 1,000. You wrap it 1,000 times and you leave it there. How many states do you get? Well, there's just one state. It's the guy just sitting there. Okay? It's not doing anything. It's just the smallest length it can take elastic band. If you wrap it, will just become completely straight and just stay there, right? There's just one state. So if you count the entropy of that, entropy is log of the number of states. So what will you get? Just 0, right? So if you had gotten a good horizon area here, wouldn't that be a problem? There would be a lot of entropy here, and the entropy here would be 0. This answer would not match with this answer. So somehow string theory is clever enough that it doesn't actually end up making a horizon if you just take a string, because see, the entropy here was 0. As I said, there are small caveats to it. It's a supersymmetry multiplet. There are actually 256 dimensional states because there's a supersymmetric partner, a fermion to this, and then there are partners to the fermions. But that doesn't matter. The log of this is still a finite number, like log of this would be something like 10 or something. But the point is, it doesn't depend on n. It doesn't keep growing and growing. While the area, normally you would have thought that if you keep increasing n1 to a million, a trillion, you can make a black hole bigger and bigger. This area would have grown bigger and bigger. Okay? So the area here is just about Planck size. With this Planck size or 2 Planck size, you can't really resolve it. So the entropy might as well be equal to this. This is just some number like 10. So, but nothing really grows, and so at least we have consistency. So we should ask why that happened. How come I didn't make a good horizon? And the reason is also very simple. Everything in string theory is completely intuitive. If you wrap a string on a circle, what will happen to that circle? Space-time can bend. As you know, space-time is completely flexible. If you wrap a string there, what will be the shape of the space-time? There's a tension of the string. Energy of the whole thing is minimized if the direction pinches to 0 size, right? Because the string has less energy, elastic band. There is some energy in the metric to bend it. So the metric pays some price to bend it, but the string actually benefits by, having to be stretched less. And if you actually work out the metric for a string wrapped on this, people know how to write that metric, and this is what it actually looks like. And because of this pinching over here, that's why the area actually goes to 0. This is the area in the compact direction, remember? But the area we actually write down here, this actually, once you have extra compact dimensions, this is the area of the non-compact dimensions, the angular area, but it also has to be multiplied with the area in the compact dimensions, because that's also area, So if the compact dimension pinches, by the time you work it out, you actually don't find any area in the overall to put in the Begistein formula. So anyway, it is really as simple as this, that the thing pinches, so it doesn't give you a big black hole, and you don't get a horizon, but that's good because you had no entropy anyway expected from string theory, and you're not getting any area either. Somebody had a hand up. Yes?
So, are you using space-time as an emergent notion from string theory, or is just classical general relativity?
It's not classical, but in string theory what happens is space-time is always there, but it's not anything emergent or anything, it's all exact string theory. So you have a Minkowski manifold, it's some metric manifold, and then you have strings, and then you are quantizing the strings in that background, and the background can fluctuate because we have gravitons. When you have gravitons, you're really quantizing the fluctuations of the metric. So if you have a graviton, you're actually doing quantum gravity. So these are objects sitting inside a fully quantum gravity theory, right? But it is true that when I'm writing this metric, because the metric is mostly classical with only small semi-classical fluctuations, I'm not writing the fluctuations. But at all times, it's very important I have full theory of quantum gravity in front of me. If I'm not dealing with quantum gravity, okay, nothing will work anyway. It's all fully quantum. So the hope is that when N1 is very big, let's say when you make a big black hole with N1 is 10 to the 40 or something, that many particles the sun has in it. So then you expect to get something pretty classical. That's what you were hoping. And if you got that, it would look something like this. Okay, so now the point is, how do we prevent this guy from pinching off? Now, if we wrap strings, we've already seen the guy wants to shrink, because if you have an elastic band, its energy is minimized when the guy shrinks. That's clear. Now, you need something whose energy is minimized when the guy expands, because then you can sort of balance it off, right? The string will make it shrink, something else will make it expand, then maybe it will actually become a nice finite guy. So, do we know anything who prefers to have the compact dimension expand? That's all we're looking for, right? So, how do we get something which will make it expand? Suppose you take a graviton and you make it go in this direction, not running around like this, but make it race around the compact circle. Then what will happen? What is the energy of the graviton? So graviton is a massless particle. In a massless particle, you know E is equal to P times C. You guys remember that E square is P square, C square plus M square, C fourth. If mass is 0, E is P times C. C is always 1 for us. So E is equal to P. But how much is it? If you have a circle of length L, then the energy of that, or the momentum of the guy, which is equal to the energy, will be units of 2 pi n over L. Is everybody familiar with this? It's just a wave. So let us actually derive this, because this is going to be very basic for us. So if you have a wave on a circle, it is something you must have learned even when studying sound waves in undergraduate physics. I shouldn't draw there, you can't see that. So if I have a circle of length L, and if I have a wave which has to go around it, then the wave has to close here. So the wavelength is equal to the total length L upon some integer. Okay, I've called the integer NP, so let me call it. P stands for momentum, because it's carrying momentum. Okay, so upon L, so that's the lambda. And so if I want the momentum, P is equal to H over lambda. So that is going to be H over L, and the NP goes here. Did I do that correctly? Okay, I can write this as H bar times 2 pi and NP over L. So H bar we normally put equal to 1. So the units I'm using H bar is 1. So then this will be equal to 2 pi NP over L. So this is just what you have learnt in elementary quantum mechanics, and see, that's the energy of the graviton. So everything in string theory is going to be this easy. You are simply going to find the energy possible for a graviton going here. It goes only discrete units and it depends on L, but you can find the energy of this graviton. Just like we could find the energy of a string, it's the mass per unit length times the length, so constant times the length. And so we know the energy of that guy, we also know the energy of this guy. Okay, but we don't even want this kind of graviton. So NP tells me roughly what is the strength of the graviton. So I have another number coming up. You see, we already had one number, which was the number of these strings. How many times I wrapped it? That was N1. Now I have another number coming up. How big an NP I take? So clearly, if I'm trying to make a big black hole, N1 I'll take to be a big number, like thousands, millions. NP also I'll take to be a big number, thousands or millions. And so I have two big numbers. I'm trying to make a big black hole. But now I don't want to just separately have this and separately have this. I want to make a bound state. Previously, we asked how to make a bound state of one string with another string, and the answer was easy. Just take the elastic band, keep going, and then join it back. But now, how do you make a bound state of a graviton, just carrying momentum, and a string? Again, everything is much simpler in string theory than it is in quantum mechanics. If you do that, this is a picture of the bound state, but we want to know what is the bound state doing, and the answer is very easy. The bound state simply means you had a string, and if you want to bind a graviton to it, graviton carries momentum. So I have to carry some momentum along the string. So how do you carry momentum on the string? You just put a traveling wave on the string. Do you guys all know traveling waves? Like if you take a clothesline, you tie it here. If you give the clothesline a jerk, then a wave goes along it. That's called a traveling wave. That's all there is to it. If you're a traveling wave on the string, then you can see I still have the string and I have some momentum going along it. So I have a bound state of something carrying momentum with the string. And that's all there is to it. Okay? So that's the picture. We write it like this. So here now this has two kinds of charges. It has N1 charge from the winding and NP charge saying how much momentum I have put. It's wrapped on a circle of length L. So I'm keeping all the numbers in here. There's the length L coming here. And if you just want to see how the traveling wave looks, let's open up the string. People call this the covering space. Like if you want to show the entire shape, instead of looking at length L, you look at the length N1 times L, just open up the string and the string just has to carry a wave. You can see I've drawn the transverse, the wave moving along the string. Does that make sense to everybody? Yeah.
So, gravitons are also strings with the excitation of closed strings.
Gravitons are what?
Gravitons are also coming from strings.
Yes. Closed strings.
So, these are defined
Okay, no, that's a good question. So what happens is if you take the string and you wrap it on the compact circle like this, that's what I have done right now. That gives me a lot of mass sitting there. Suppose I don't wrap it on the compact circle, I just leave it like this. Then I said it will shrink to zero size. It will have no mass. That's the graviton. Okay, so the graviton is a shrunken state of the string. That's the graviton. I can then give it some momentum if I want, but it's the ground state of the string. Okay, even here I can.
I think his question was, how can you have that on top of that string? That is his question.
How can I have both?
Yeah, so because he wanted both the charges on the string.
Yeah, okay. So I can have both because I can take this graviton and this is massless, but I can also make it move. I could make this also move. Anything can move. If anything is stationary, it can also move. But the question is, if I have something which is moving, and suppose I make it move in this direction, I have a graviton moving in that direction. That's what I was drawing here. The graviton moving in that direction is the blue guy here. Then I can still ask if this string collides with this string, what does it do? It will still have the winding because the string can't just break. It's still there. And something has collided with that, which is carrying momentum in that direction. There's some chance they'll bind to each other. If they bind, what will it look like? It still has to be a string because the string joining to a string just gives another string. Right? Two string loops join, they just make a longer loop. It's a string which is carrying momentum. Now just think about what it could be. It's just a string carrying a vibration. So if you actually go to string theory, like open up a textbook and do string theory calculations, you can calculate this. You can take a string with just winding and no momentum. You can take a graviton carrying momentum and no winding. You can do the 3-point function for one to be absorbed into the other, and you'll actually create this string state which I'm drawing in pictures. It will be a string carrying a left moving vibration. Okay. So it's just elementary string theory. This is the elementary string vertex. But we just need pictures, so I'm just drawing pictures. But yeah, you should keep asking if you know some string theory, then we should keep connecting back to your string theory. Okay, so is this picture clear that I just opened it up here to see that? So if this string was wrapped 2 times, I can just look at length 2L, and then the 2L I can see this shape going. So why is it good to imagine it opened up like this? Because the only constraint on this guy is that after it goes length 2L, or in general N1L, N1 times L, then this guy has to be closed up here. Is that okay? It has to join back, right? It's a closed string. So after I go length N1L, it has to close back. Before that, it doesn't have to close. That's very important. And then in this, I can choose any shape I like. And then all the different shapes will give me all the different ways of carrying this momentum on here. Okay. So how much momentum am I carrying? Let's go back again. Total momentum I'm carrying is P, which is 2 pi, some integer upon L. Okay. And now what's the total length of my string? If I open it up, it is N1 times L. So you can see these numbers N1 and NP are both playing a role here. And so now let us ask, how many states are there here? Our goal always was to count the number of states because we are looking for entropy. So now we have made an object which carries not only string winding charge. We first tried only string winding. That wasn't working to give us a good black hole. Then we said we'll take winding and we'll also add this momentum to it, NP units of momentum. We'll try to see what kind of object it creates. But first let's count what's the degeneracy this time. If I only had the string, there was just a unique state. It's just sitting there like elastic band at minimum length doing nothing. This time it's an elastic band but carrying traveling waves. How many states do I have? You can already see there are many states because there's many ways to put the same momentum on this string. Can people already see that? Because you can choose different harmonics. You can put them all in the lowest harmonic, or you can put some in the lowest harmonic, some in the second harmonic, put all in the second harmonic, some in the fifth harmonic. There are many ways to partition it. There are many ways to partition the total momentum among different harmonics. So this is nothing to do with string theory. You can go and just take a rubber band at home and just play with this. You take maybe take a guitar string and tie it from here to here. And with the same amount of total momentum you want to put on the traveling waves, you can do it in so many ways. You can take the lowest harmonic and make it go, but then you need a large amplitude. Or you can put something all in the second harmonic, lead slightly smaller amplitude because the second harmonic has more energy. Or you can put some in the first harmonic and some in the second harmonic. You can mix harmonics, right? You can make a complicated thing. All those are different ways of carrying the same mass and charge, total energy and total momentum on the guy. So if you're counting the entropy means for the same total amount of charge and energy, how many states do you get? You can already see you're getting many, many different states. If I can count them, I will get the entropy of the black hole this time. Okay, so let's do the counting. So again, this is the same picture. The length is N1L. There are N1 units of winding, NP units of momentum. And now let's try to do the counting. This is the crucial step because if you can follow this calculation, this was first done by Ashok Sen. A small extension of this will be the Strominger-Vafa calculation, and you will know everything about the entropy of the black hole. Okay, so this elementary calculation, which is again just textbook quantum mechanics, will tell you everything that you need to know. So you should keep asking me till this is completely clear. So where's my eraser? Okay, so if I have some string on a circle of length, the circle length from here to here is, I call it L total, right? L total is N1 times L. That's my total length over here. So in that, I can choose something in the, so K equal to 1 is the lowest harmonic. What does that look like? That looks like this, right? K equal to 2 is the second harmonic. That looks like this. So you can put it in any harmonic, right? So if you have a single quantum in the harmonic, in the lowest harmonic, what is the momentum? Let's do that. So let me erase all this. If I choose the wavelength which is just one oscillation from here to here, how much momentum does it have? We had the calculation. The momentum carried by this guy, which is the same as the energy, it's all a massless particle, E is equal to P. 2 pi n over L is now L total, right? The length of the total string is L total. So 2 pi integer over L total. If I want the lowest harmonic, I put n equal to 1. People remember that? 2 pi n over L was the energy. So if I take the lowest harmonic, its momentum will be 2 pi over Lt. So there will be nothing. Next one, what will I get? E equal to P equal to 2 pi over Lt times 2. The next one, so that will be for this harmonic. So a single quantum in that harmonic has 2 pi 2 over Lt. In the third harmonic is 2 pi 3 over Lt. Just the way you do waves in quantum mechanics. So a quantum of the harmonic K has momentum 2 pi K over Lt. Is everybody comfortable with that? So the total momentum was 2 pi np over L. You guys remember that total momentum we put was 2 pi some integer over L. Okay. I'll write that momentum as 2 pi. L is equal to, so Lt is N1. So if I put an N1 on top and N1 on the bottom in this formula, I can write like this and I can put Lt over here. So why did I do it like this? Because really I have to partition thing, my total length is actually Lt. So I just prefer to write it like this. So now you can see the total momentum I need to carry is 2 pi, this integer upon Lt. Okay, so now it's at least clear how to count all the harmonics. My total amount of harmonics, like if I put some quanta in harmonic 1, some quanta in harmonic 2, the total number of units has to total to N1 NP. So let us just do that explicitly for a few examples and then it will become clear. So these N1 NP units have to be partitioned in different ways, and so this is the formula that we need to understand. Okay, so what are we doing here? Suppose in this particular string, so here's a question for you guys. Suppose I put 3 units of the lowest harmonic, K equal to 1, and let's say 5 units of K equal to 2. What is the energy of this? Does everybody want to think about it for a minute? Okay, so the energy which is equal to the momentum of this is going to be 3 units times whatever is the cost of the lowest harmonic. Lowest harmonic is 2 pi over L total, because L total is my length. And then I have 5 units times 2 pi times 2 over Lt, like this. That's the energy of this guy, right? So what do I need to do? The number of units in the lowest harmonic is, suppose I call it N1. So here N1 was 3. Then times 2 times the units in the next harmonics, there N2 was 5. 3 times the units in the next harmonic, because the other harmonics are more expensive. So all these numbers have to total up to the total amount of energy I need to put, because my total has to equal what? My total momentum has to equal 2 pi N1 NP over Lt. So I'm getting all units of 2 pi over Lt. Do you see the 2 pi over Lt coming everywhere? 2 pi over Lt, 2 pi over Lt is all there. 3 times 1 plus 5 times 2 and so on. If I keep adding them, they must equal this particular number. So then you find that what I need is, all these numbers should equal N1 NP. These numbers are fixed. I have chosen N1 units of string winding, NP units of momentum I want to put. So I choose them, maybe 1,000 of these, maybe 5,000 of these. So this number is some 5 million. Now all the different ways to make this number match up to 5 million is an allowed state of the theory. So you have to count what are called partitions of 5 million, all the different ways of summing K times Nk. K times Nk means 1 times N1 plus 2 times N2 plus 3 times N3. A schematic way of writing this, that should equal this particular number, which in our case was 5 million. Okay, so how many numbers are there like this? If I gave you some number, if I gave you a number like 10, and I told you to break it up into all kinds of pieces, how do you break it up? They can be all in the lowest harmonic, so 1 plus 1 plus 1 10 times. You can also do 2 plus 2 plus 2 5 times. Or you can do 1 plus 1, that's 2, and then 8 I can get as 2 plus 2 plus 2 plus 2. All these are different partitions. Okay, or you can do 5 plus 5. Or you can do just 10. Okay, so count the number of possibilities. That looks like a lot of possibilities. It's interesting that people have figured out the number of those possibilities. If you want to find all the different ways to break up this particular number, the number of those possibilities is e to the power 2 pi, whatever number you want to break up, upon 6 square.
The first n word is not the same thing as the n word.
I realize that confusion. I apologize for this. This is not the n1 I was using for number of strings. I should have called this something else. Thank you. So this is an interesting formula. It just says if you want the partitions, so the number of partitions of some number, I'm running out of some number m, which is not the mass or anything. Then the number of partitions, which I'm calling n there, is e to the power 2 pi square root of m over 6. You can see it grows very rapidly. If m was 1,000, then this is roughly like, if m, 2 pi and then e to the power some 30 or something, that's a huge number. Okay, so it grows very rapidly. That's good because we are going to try to use this for the entropy of a black hole. And we said the entropy of black hole is huge, so it's good it's coming out to be huge. This formula goes all the way back to, more complicated versions and more exact versions of this formula. This is the leading order answer. This all comes from the work of Ramanujan and Hardy. So it's very, very important and beautiful mathematical work. But anyway, once we have this number of partitions, for physics purposes, we just want to compute the log of that number because that's the meaning of entropy. Okay, so we have found the entropy of an object in string theory, which carries a string winding and carries some gravitons bound to it. We've made an object in string theory and we have been able to compute its actual entropy. Now this was all at weak coupling. How do I know at weak coupling? Because I'm just taking a simple picture of a string vibrating and all this is just free strings. There's no gravity, it's not like gravity like attracting it or squeezing it or doing anything. So this is a weak coupling calculation. Okay. So as I said, our trick will be to do everything at weak coupling, and if we can do the weak coupling, then we can try to see what happens at strong coupling. Yes? The formula is true when n1 np is much bigger than 1. I didn't hear that. Can you repeat, please?
This formula is true if the product of n1 and n is large.
Yes.
So what are we assuming to be large? Is the binding is large or the Wenda and is large?
So here either can be large. Typically they are both large because if you want to make something like a good black hole, you will take n1 to be millions and np also to be millions. And then the product is obviously large. But as far as mathematics goes, it only cares about the product. You could even take n1 small and np large or np small and n1 large. The formula will still work. But for the black hole we want to make, everything is large. Like if you want to make a big black hole, you put everything too many. Yeah. Okay, so at least we know what we should count and how to go there. There's a little bit more work we have to do to be more precise because these vibrations we put, there's a little bit of extra stuff in it. If you have a string which is vibrating, you can vibrate in this direction or you can vibrate in this direction. It's a transverse vibration, right? You can put going this way or you can put going this way. So if there are many transverse directions, it can go in any of those directions. That also increases the entropy because there are many possibilities. So when I said you put the lowest harmonic, it could be lowest harmonic vibrating this way or it could be lowest harmonic vibrating this way. So let's take that also into account. It's not a big change, but it's something to take into account. It turns out that for every extra direction, suppose you had, let me just write the formula here. So suppose you had f directions of vibrations. Then the answer for this is e to the 2 pi root m over 6 and there is an f. Okay, so if f is 1 then the old formula is true. If f is a bigger number, you can see the answer goes up. But you expect it to go up because there are many directions, so it goes up. Okay. Okay, so you can see we are being very precise with even the factors of, there's few, there are not that many directions, they're only like at most 8 directions transfers to you. But we are being even very precise about this because we will in the end match the entropy down to the last 2 and pi, right? So that's why we want to be completely precise about everything. Okay, so if you do that for what is called type 2B string theory, let's see if we can get an answer. So let's get the exact answer for this. So if you are in 10 dimensions, so 9 plus 1 dimensions, then one direction the string is wrapping in that direction. That's the length L, right? So the string is wrapping in this direction. So the transverse vibrations go in these directions. So how many transverse directions are there? Can somebody look at this and tell me? 8. Because only 9 space directions. This one is time. Out of the 9, 1 is gone here. Number of transverse directions is 8. So 8 transverse dimensions. So you might think that I should put F equal to 8, which is almost true, except this is a supersymmetric string, so there are also 8 fermions. There are 8 bosons and 8 fermions. And there's a general rule, so 8 bosons plus 8 fermions. And when you start counting this for fermions, we just counted for bosons. This counting was very simple, just ordinary vibrations. It turns out that each fermion counts like half a boson. Now this is not difficult to do. It is just an elementary calculation. If we had a few more minutes, we could actually do that. But for the moment, just take it from me that if you want to look at the fermion counting, it just counts as half. So this counts like 4 bosons. So then I get a total of F equal to 12. So let me just say a few words about where would you go and learn that a fermion is half a boson. If you just go back and see how to fill up the fermions, like the bosons and fermions, what's the difference? Like if I do all the excitations, I can put, let's say, 3 quanta in the lowest harmonic and 2 in the next harmonic and like that, right? Can I put 3 fermions in the lowest harmonic? No. I can only put at most 1. So you've got to start counting from scratch. Like in each mode, you either have 0 or you have 1. Not like in each mode, you can have anything. Okay, if you just do the counting for that case, you come up with this answer, that a fermion counts like half a boson. Okay, so that is not completely obvious. Each direction of vibration is like a boson because we just said it's a quantum of vibration, and you can put 1 quantum of vibration or 2 or 3, so that's why we call them bosons, because you can put any number you like, right? And they're all identical digits. You can just put them. Now the fermions is less clear because we haven't even talked about where the fermions are in the theory. But every time you have a string in some configuration, you can also add a fermionic field along the string, which is there in, so if you have a string which is vibrating, how do you describe the vibration? I'll write it up here. You describe the vibration by giving a profile which is x as a function of, what shall I call this coordinate? Shall I call this coordinate sigma? If I give you x, the transverse displacement as a function of sigma, that describes a traveling wave. Is that clear? Because the amplitude. Okay. So this is just an ordinary bosonic function, x as a function of sigma. There's also a function psi as a function of sigma, which is a fermion. So on the string, there will be 8 x's telling you each of the 8 transfer directions of vibration. There are 8 x's, but there are also 8 psi's. But because we haven't done this whole string theory properly, we don't know that yet. Okay. But the total string is described by giving the profile of vibration of 8 x's, but you also have to give 8 psi's. That's because it's a superstring. If you're for the bosonic string, you wouldn't have to do that, but it is a superstring, so that's also required. Yeah.
Why can we consider the vibrations also in the non-compact direction? Like why all of the 8?
Oh, I'm sorry. I shouldn't have said compact direction. This is all the 8 transverse directions. Right now, they're all here.
So all of the transverse directions, be it compact or non-compact, can be included?
Right now, they can be included, yeah. You can wrap the string only in one of the compact directions, but it can vibrate any way it likes. It's just the direction of vibration, right? It doesn't care if somewhere you go is periodically identified or not. You can vibrate anyway, so I'm include all the 8 transverse directions. Yeah, absolutely. Okay, so let's put this number f equal to 12 in here, and then what do we get? So the number of states was equal to e to the 2 pi square root of n1 np over 6, and then I have to put 12 here, the f. So 6 and 12 gives me 2. So it becomes e to the 2 pi root 2 root n1 np. People okay with that? And so what is the entropy? The entropy is the log of number of states. So the entropy is going to be equal to log of n, which is 2 pi root 2 root n1 np. Okay, and that's the answer which is here. So it's very precise. These things can be done very well. You can just count how many states of a string. you take some states and you can just have free strings and you can count what's the degeneracy of the bound state. The degeneracy of the bound state is simply coming from the fact that you can partition the energy in many different ways. And it's a little bit like when you have the hydrogen atom. If I ask you for the degeneracy of the, n equal to 2 level, so you know how to count it, right? You have at n equal to 2, you can have L equal to 0 and 1. There are 8 electrons that fill the shell. They all have the same energy. That's what we call degeneracy. So the corresponding analog of that there are 8 electrons in the shell. The lowest shell can have 2 degeneracy. The next one has 8 degeneracy. The analog of that, if you have n1 strings and np these things, and you make a bound state of that, just like it bound state of proton and electron, that had degeneracy 8 for n equals 2. This one has degeneracy e to the power this much. So if you want the entropy, that's the answer. And look, we just derived it. So the only thing here we have assumed, which we didn't know, was these partitions. But if you have a little small computer, you can easily make yourself a computer program to count these, and you can easily check this thing is true down to the 6. Okay, it's a very cute little program you can try to make, and you can see these partitions work out very nicely. Yeah.
Sorry, I'm not sure from where does the 6 come from?
Oh, this formula? So that's what I'm saying. That's the one I have not derived for you, and that's the one you can, either go back and derive it from the Hardy-Ramanujan formula, wherever they got it from. But that's somewhat high-powered mathematics. But I was saying it's great fun to just go and play with it with a small laptop, and you can set up a small mathematical program to count all the number of ways that if this is some total, I have called it m here. This is some number m. You just put m equals 1000, and you see all the different ways to break up 1000 into different pieces, like 1 plus 1, 1 plus 2 plus 3, or 3 plus 2 plus, all the different ways to break it. And you will find the number of different ways of breaking it up to come to the same total will actually satisfy this formula. So you can just check it on the computer if you like, just for fun. That's all I was saying. I did not give you a derivation of this, but for the moment this is just mathematics, so we are taking it. Okay. But so using this, we have this. If you have some other theory called heterotic string theory, you can use this. We are not going to actually deal much with this, but the original work of Ashok Sen was, in this case, it's just the factor is a little bit different, because heterotic string has more transfer directions of vibrations, more effective number of transfer directions of vibrations. Okay, so it's just the F is different, so the answer is a little bit different. But we will just stick with this for the most part. But this is the important work of Ashok Sen in 95, which basically triggered off all the work in black hole entropy. This is the first time anybody got an entropy coming out of string theory for black holes. So that's why it is so profound. Before that, nobody knew what to do with black holes. And the black hole is just sitting there, doesn't seem to have anything to count. But now at least there is something to count, and there's such a precise number for it. Okay, now let's go back to see what geometry we create. Last time when we tried to look at the geometry, we got into a disaster. It made a singularity with no horizon area. It was all completely gone. And this time what happens? So this time now we have two kinds of guys here. And the weak coupling picture, there are strings and vibrations on it, and the N1 units of winding and NP units of momentum on it, and all this picture. And then if you actually do this properly, in that heterotic case, these guys sort of did the thing properly after a little while. It turns out you can actually find the area of this horizon. It's slightly tricky because when the horizon is not very big, in this case the horizon is not very big. In the previous case it was really 0. This time it's a little big. But if it's very big, you have to be very careful of all kinds of stringy corrections. Instead of the Beckstein entropy, you have to compute something called Beckstein-Wald entropy. It's not exactly A by 4G, but in this case it works out to be A by 2G. There should be an equal to sign here. But it turns out if you work out the analog of the area entropy for this case, it exactly matches what Ashok Sen had computed. Okay. So what is good about that? What's good is that we really seem to be understanding black holes in this very simple way. At least at weak coupling we can count all the states. At strong coupling we can find the metric it creates. From there we can get the area. And the two are exactly matching down to the last factor of 2n pi. Okay, it's an exact match. There are some things which are not completely fine with it though, because this black hole, it has some size, but the size is compared to the size of a string. So if you leave a string in the relaxed state, we said it becomes size 0 if you don't do anything. But it's not exactly 0, it's like Planck size. So it's actually what we call string length. So that little size string length is actually comparable to this size. And so then you have to be a little bit careful, and that's why all these corrections came, this A by 4G plus A by 4G and so on. But anyway, you can do it properly, and it does work out, but it's a little delicate. So people said, let's try to make even better black holes, which is the Strominger-Vafa black hole that I'll talk about now. But let me just see if we can really absorb the lessons here. So the one step here which was very important in Ashok Sen's work was that all the black holes we made had mass equal to charge. You guys remember that story? Every object in string theory has mass equal to charge. What is good if mass is equal to charge? If mass is equal to charge and the black hole is what is called a supersymmetric black hole. It preserves some supersymmetry. If it is a supersymmetric black hole, then the number of states it has does not change when you change the coupling. Now that is crucial because the only time we can actually do the calculation is at weak coupling. This kind of traveling wave picture and all that, that's a weak coupling calculation. At strong gravity, we had no clue what to do. Okay? So if the number of states change between weak coupling and strong coupling, we would still be nowhere because we compared weak coupling, but the black hole is there at strong coupling when the gravity is all strong and making a horizon. If we can't count in that limit, we are again done for. But the point is the number of states doesn't change because supersymmetry, so we actually automatically have a count of states as strong coupling even though we don't know what the states look like. They look like this, just traveling waves on a string at weak coupling. We have no idea what they look like at strong coupling. But we already know that if we compare that with the area of the normal black hole that people make for that much mass and charge, if I give you a mass and charge, you can make the metric. Everybody knows how to make it. And you take the area of that, the answer matches perfectly. So this is beautiful because this theory of quantum gravity, string theory is so beautiful that even the last factor of 2 pi and all is exactly fitting, and that magical entropy has come out down to the last factor of 2 and pi, except we don't actually know what the states look like. We don't know what's going on inside the black hole, but we got the entropy. Let me just pause here to see if there are any questions, because I'll switch gears to the 3-charge black hole now. Yeah.
So where does this 4 pi root n1 effect factor come from? Because a by 4g plus a by 4g will be a
So this was a typo, as I said. There's an equal to sign here. So this is the correct entropy. It's a by 2g in this case. It's equal to this. And then this was exactly the answer Ashok Sen got in his 95 paper. There's an equal to sign missing there. Okay, this is good with everybody? Okay. So a tremendous achievement actually for string theory. Okay, so then people said, can we make a black hole whose horizon is a little bit bigger so that it's not like the same size as the size of a string, so that we can really completely make sure that this thing really works? And then they said, okay, so far we put 2 charges. What does that mean? We had string winding. We had momentum on it, something gravitons bound to it. Can we stick in one more kind of object? We have so many objects in string theory, let's stick in one more guy. Okay? We already see the pattern. When we had 2 guys with n1 units of winding and np units of momentum, the entropy is proportional to n1 times np. You guys remember n1 times np coming? The beautiful thing will be when we include one of these brains, we'll actually include the 5-dimensional sheet. Okay? So the number of those we'll call n5. The entropy will be n1, np, n5. It's very simple, always works like that. You just multiply the different guys and that's the entropy. Okay? So we just have to understand how that comes. If we can derive that and we also get the 2 pi factors for it, that's the famous Strominger-Vafa result. So you already know all the tools, we just have to go and do that next part. For that we just need to know one more property of string theory, which is actually quite interesting and deep perhaps, and we just want to learn it. So let's learn the following. Suppose you have again this compact dimension of length L, and this is my non-compact dimension. See, the picture is familiar, right? The same thing we've seen all the time. And we said if you have a graviton going up, you can sort of make it go around. If you have a string here, you can put traveling waves going one way. You can also make traveling waves going the other way. Is that okay with everybody? You can do that. You can make them go both ways. Okay. What's the minimum energy for a traveling wave's excitation you can put on a circle of length L? So why did I put them in both ways? This one carries momentum, but if I put some going up, some going down, the net momentum can be 0. Let's do that. Let's put net momentum 0. But it does have an energy because this and this, the energy adds up. The momentum is opposite, energy adds up. What's the minimum energy for exciting a string? So that's the basic question. It's called the energy gap. In any system, the minimum energy required to excite it is called the energy gap. What is the minimum energy required to excite a string? Let's think about that. So a graviton has energy 2 pi k over L. The lowest energy you can have is 2 pi over L. Do you guys remember that story? 2 pi over L. So this guy has energy 2 pi over L. This guy has energy 2 pi over L. So the least energy I can get is 4 pi over L. So that is the energy gap for a string. Okay. Something very interesting happens if you take not a singly bound string, but a string which is n1 times wrapped. Remember we had wrapped it n1 times? Okay. What's the interesting thing? So if you have a singly bound string, the energy gap is this much. 4 pi over L. So k equal to 1 is the lowest gap, but then k equal to 2, 3, 4. Those are the higher energy gap, but we don't need them right now. If you have n1 winding, then what's the lowest energy? Now we see the string actually has length not L, it has length n1 times L if you open it up. And the wave has to close only after the full string. So the wavelength is actually very long. And the wavelength is longer wavelength means lower energy. So the energy gap now is 2 pi over n1L, 2 pi over the length of the new string, the long string, and the other way around, going the other way also, is 2 pi over n1L, and the energy gap is this. Okay. So do you see something interesting? If the energy gap of a single string is 4 pi over L, energy gap for a multi-wound string is 4 pi over n1L, which is smaller. This is smaller. So if you bind many strings together, the energy gap becomes very small. Okay. So what is the lesson over here? How did it become small? What's the magic here? How did the energy gap become small? And the magic is that if you put a graviton, so let's look at this picture. If you have a graviton going on a circle of length L, what was the energy of this graviton? It was 2 pi over L. So we've done this multiple times. It was on this slide also. If you put k equal to 1, a graviton has energy 2 pi over L. But if you put the graviton and you bind it to all these strings, what is its energy? What's the minimum energy of a graviton? If you bind all these strings, you have to open up the string to a length n1 times L. And the graviton only has to close after that much. It can have a much longer wavelength. You see, here it has to have a wavelength that ends after L. It has to be periodic over L. If you join it to n1 strings, it has to be periodic after n1L. Its wavelength goes down. Okay? So wavelength goes up, energy goes down. Why is this so crucial? We're going to find that all the magical effects of string theory as to how quantum gravity goes from Planck length all the way up to horizon size is all traceable back to this effect. That by itself, every object has a certain natural energy scale, like 2 pi over L or something. But when you bind it to a lot of different guys, it comes in what we call fractional units. Instead of energy 2 pi over L, is 2 pi over n1L. If n1 is a million, it comes in very small units, 2 pi over a million L. Can you see it looks like a very small piece of a graviton now? And that's the magic. If you make a big black hole, these numbers n1 and so on will be very big. And then all the objects come in very small pieces. And that's how somehow they can become very light and they can go to big distances, and that's how somehow the whole black hole structure will change. So this very elementary fact, which is just quantum mechanics, is at the root of everything. So we just want to see it. Okay. So now we already said that a graviton by itself comes in units of 2 pi over L, because the wave has to close after length L. When it is bound to n1 strings, it gets fractionated, and then it comes in units of 2 pi over n1L. We just said that in pictures. Is this okay with everybody? Okay. So this looks like a simple phenomenon, but now you can see how interesting it becomes. Suppose you take these one-dimensional strings and you stick them into 5-dimensional sheets. We haven't talked about this so far, but let's have fun with it. Take a 5-dimensional sheet. We haven't used it so far, but now let's use it. We had these one-dimensional strings. We can stick it in there. What's the mass of this string? It's the mass per unit length of a string, which is pretty dense. It's about Planck scale, right? So mass per unit length, and then multiplied by the length. If you stick it there, that's the mass of this guy. Then it turns out that you can do these dualities. I was telling you that anything can be mapped to anything in string theory. I mean, duality can map anything to anything by symmetry. So you can map this guy to this, and you can map this guy to this. Okay? Now you can see why it is so interesting. If I take one of these guys by itself, it has units which come in some 2 pi over L. This has a mass which comes in some units, tension times the length. If I stick it to many of these strings, you see this comes in fractional units. So if I take many of these D5 branes and I stick this in, this will come in fractional units. So just like I could think of a fraction momentum, that was just ordinary things of waves, if you're completely comfortable with, I now see I can get fractional strings. Okay, so that's the important part. When you stick some strings into some kinds of branes, they just become fractional. So we'll just do that and we'll get the answer in a second. Whatever I said is now in these slides. When a graviton binds to n1 strings, it breaks into n1 fractional units. That's what we said here. When a d1 binds to n5 prime d5 branes, I just put primes because I just dualized everything, it should break into n5 prime fractional units. So this string by itself has some mass per unit length. When you stick it in here, you see it becomes into lots of different lighter, thinner strings. Okay, it's just duality. So here it was completely clear because this was just ordinary lab physics. A string wrapped, a longer string has longer wavelength things. The moment you look at dualities, you find if you have, let's say, 20 5 branes and you stick one string in it, it will break up into 20 fractional strings, each of which has tension 1/20th of its value. That's very interesting because strings had a tension of Planck scale, and so they could never stretch very far. But the moment you join them to 20 D5 branes, the tension becomes 1/20th of their value, and now they can go not up to 1 Planck length, they can go up to 20 Planck lengths. And now do you see how this magic will work? If you bind it to 1 million 5 branes to make a big black hole, the potential will become 1 millionth of a Planck length, and now they can stretch to 1 million Planck lengths. And that's how these guys will always have a quantum gravity effect that goes all the way to the horizon. So that's the key to how this thing works, but just duality applied to what you already saw. Okay, so let's do our picture now. Let's do the calculation. Let's take n1 prime of these guys. I put primes on everything because we're doing a different picture, again, starting from scratch. And I have n1, n5 primes of these. When they go in here, how many guys will I get? I have each guy breaks into n5 prime pieces. I had n1 prime of these. They break up into n1 prime times n5 prime fractional branes. Okay. See, string theory is all just pictures. There's no hard calculation. Okay. So then I can do lots of things with it. I can join them all up into all the little branes into one long string. Can you see how long this will be? This length is L. But now if I have this much winding, it's a string of length n1 prime, n5 prime times L. It's a very long string. Okay, but it's just a long string here. We can join these fractal branes into one multi-wound effective string. There I have joined it. And now let's go back and put the third charge, the momentum, on it. Can you see now I have bounced into 3 strings? Earlier I had strings and I had this momentum on it. Now I have strings, momentum, and I have the green stuff, the 5 branes. Look, I've got 3 guys. Everything is just pictures. This is called the D1, D5, P extremal hole. This is the Strominger-Vafa black hole. It's made of 3 kinds of charges. 1 branes, 5 branes, and momentum. Okay, everything is simple. Okay, so now let's just go and do the calculation. We have n1 prime D1 branes wrapped on a circle of length L. We have np prime units of momentum along the same direction. This is the momentum, this is the 1 branes. n5 prime D5 brane, those are these sheets. They're wrapped on this S1, and they're wrapped. So this is a 5-dimensional thing. One dimension is here, the length of that is L, but I need 4 other directions. It's called a torus T4. It should have some volume, I just called it V. So all these are numbers, and these are choosable, right? How the compact dimension is a free parameter. In the end, it should all cancel out. But let's see all the numbers which are coming in. The string coupling, we have already called it G. The string tension, the mass per unit length of the string, is normally called T. Sometimes people write it as with a new parameter 1 over 2 pi alpha prime. You don't have to pay attention to any of these. We don't need this. And let's see what we get. Okay. So what entropy do we get? We have this string which had a winding number n1 prime, n5 prime. Its total length is n1 prime, n5 prime, L. Remember last time the unit was n1 L. This time it's n1 prime, n5 prime, L. Because I have more objects in there. Same story as before. Now I want to put the transverse vibrations. A quantum of harmonic K has momentum 2 pi K over L total. Exactly the same as before. It's just that L total is longer. Can you see the rest of the calculation the same? I just have a longer string. On that I'm going to partition this many units of momentum. So the total momentum is 2 pi np prime over L, which I can write as 2 pi n1 prime, n5 prime, np prime over L total, because L total is this. It's exactly the same, except whenever I had n1, now I have n1 and n5 both. I have to again do the partition, but this time I have to partition what? I have to partition not n1 np, I have to partition n1 prime, n5 prime, np prime. You can see why I put the prime, not to confuse the previous problem, but otherwise exactly the same thing. And the entropy is going to grow like this, except the number here, which I have to partition, has got 3 things in it. It used to be n1 np, now there are 3 things. How many of these directions f do I have? Let's go and check that. How many directions f do I have? It is slightly different from last time, but only slightly. And once we put that, we already will get our final answer. Okay, so I'm almost out of time also, but then we'll also be finished. Okay, so now I have these 5 branes, and in that I have this string wrapping like this. But this string is now glued to the 5 brane. So it's a 5-dimensional sheet. One direction is here. This is the direction of length L. And how many directions are perpendicular to it in this 5 brane? 4. So how many directions of vibration do I have for this string? It is glued to the 5 brane. So it can't come out of the 5 brane. So how many directions do I have vibration? 4. Okay, it can go in the string, in the 5 brane any times. So F is equal to how much? 4 bosonic plus 4 fermionic. 4 fermionic counts as how much? 2 bosonic. So F is equal to 4 plus 2 is equal to 6. Okay. You can see how precise everything is. I'm going to put 6 in there. Let's see where I am. I put 6. C is 4 and then a half of 4, that is 6. Right? We already said that. So if I put it in, can you see I get my 2 pi? I have this number what I called F is actually called C here. Okay, don't worry, it's called C here. That C is 6, this cancels, N was this product, and there it is. That's my number of states. So what is the entropy? This is the log of that, that's this much. So the entropy is log N, there it is. So let's summarize what we have learned. If I make a bound state of 5 branes, strings, and momentum, if you can't resolve the compactation, it looks like a blob carrying these 3 charges. And at weak coupling, this is the picture. We have counted the number of states. This is the degeneracy. Supersymmetric black holes, same number of states should happen at strong coupling, even though we don't know what they look like. So I should now go and make a black hole carrying all these charges and measure its area. People made that black hole and they found the area A. This is a nice big black hole, there's nothing wrong with it. You can compute the area. How are you going to compute the area? You're going to go back and open your textbook for the formula for a black hole. The only thing you need to know is what is the mass you need to put. How do you know the mass? You know the number of these branes. You just need to know the mass of each brane. So what's the mass of each brane? The mass of a string is the tension mass per unit length times the length of that circle. So just like that, you'll put in the mass. What is the charge? You have to know the number of branes is this. You have to know the charge carried by each guy. Like if you're an electron, if I give you number of electrons, total charge will be how much charge each electron carries times number of electrons. So those parameters are fixed in string theory. You put in those parameters, you get the total charge, the total mass. You make the metric from your standard GR textbook for that mass and charge. You compute the area and you find this answer, and it's exactly equal down to the last factor of 2n pi. So that's the famous Strominger-Vafa result of 96, which really confirmed for people that string theory is working completely beautifully. What's amazing is that all these things like the length of this compact circle or the area of this torus in these transverse directions, it all beautifully cancels out and gives you the right answer. Somebody had a hand up. Yes?
In the previous slide, you had somehow written central charge. So is it somehow related to central charge?
It is. Because F was called number of directions of vibration. It's a, roughly speaking, number of degrees of freedom. Because each time you can vibrate, that's a degree of freedom. Central charge is nothing more than degrees of freedom. That's the meaning of central charge. So this is the same term as central charge, and if you want to be technical, you should really call it C, and C is the central charge, and it is the same thing.
So in this picture, everything is embedded in the D5 brane.
Everything is embedded in the D5 brane. It's a bound state. So just like when you had vibration mode, you could say the vibration is embedded in the string. It's joined to the string. Now it's joined to the 5 brane. You're just joining things to more things. But the pictures are all simple. Everything is pictorial, and everything, the answer is all simple. And the simple method always works down to the last factor of 2n pi. You don't need anything sophisticated. And so we have our exact answer. Okay, so let's see where we have reached. What?
The Strominger-Vafa's calculation was through the symmetric product. They didn't have the fractionization. And they had a symmetric scalar model.
Yeah, so right after that, the whole thing was simplified in the language I just used by Karen Maldacena just about a couple of months later, right? So this is the simpler picture, because they used K3.
The symmetric product is quite important, otherwise the holographic structure won't work.
So the symmetric product. Okay, so let me try to understand what you're saying, because if I go back to the picture of this effective string, if I just use the effective string and I assume that all these strings are identical to each other, right? Because two strings are identical, right? I lose nothing. Everything is here. Symmetric product I use only for the fact I have to use the fact that different strings are identical.
There what happens is the central charge gets lifted. I mean the symmetric product is such that the central charge changes. And here the length of these, it's slightly different.
No, so it turns out that you have both kinds of states. And so what happens is that, maybe I can go to one of the pictures I had here, just a little bit before. Yeah, so you can either join them all into one piece, or you can have all the pieces where they are actually not joined into one piece. They could be all separate or joined into bunches of different sizes, right? And then you could partition the momentum among all these different guys. So in principle, all those states are there. And the central charge for all of them is actually the same, because central charge is just the number of copies total. So whether they're joined together or not, the central charge is the same. So in the symmetric product language, I can keep exactly the picture I have here. The only thing is I have to use the fact that the strings are all identical. Then I lose nothing. I can use the Karen Maldacena picture, assume they are identical, and so if I want to compute, for example, the actual index for this, I have to use the fact that both the pieces which are broken up and the one where it's maximally joined and all the ones in between all have to be included. They don't have to be only the longest string. And that kind of information sort of gets buried if you try to use the formula that they used in the initial paper. But this picture actually gives you all the answer.
I mean, I'm just
Yeah.
wondering how the holography
Yeah.
the holography will work, because the chiral primaries,
Yes.
the symmetric product matches with the supergravity states.
Yes, yes.
Here, that
No, you definitely have the picture. So let's try to see where the chiral primaries are.
Are you saying that various bigger the T4?
No, it has, but the chiral primaries come from counting the chiral primaries of the
Yeah, so let's count them. So I'll show you where the chiral primaries are. So first we have to start with just ADS3 cross S3 cross T4. Pardon?
in this picture.
Yeah, I'm showing you in this picture. So let's just first how to make this. So this is made from just having D5 and D1. So I have no P in it, I just have D5 and D1. And so I have total number of fractional strings which are N1 prime and 5 prime. That's the number of copies. I haven't yet put the momentum, so NP prime is not even here. Okay. So in this case, what is the global ADS vacuum and what is the single chiral primary? So we can write them both down. And actually you know this very well because you've written so many papers on this. So the global vacuum of ADS3, the vacuum of ADS, is given when all these copies are separate and they are not joined. So that's the vacuum. And if you want the chiral primary, which is, let's say, a chiral primary of the dimension and charge J and J, then that's given by taking one string of winding J and all the others singly wound. Okay. So that's the chiral primary. So in this picture, everything has to work because otherwise the picture would be incomplete, and the chiral primaries absolutely come out this way.
So the cyclic objects, the longest cyclic object is the highest.
Is the highest chiral primary, and that has charge N1 and 5 over 2. Okay. Okay, so let's see where we are so that we can close up at a point that we can pick up from next time. So we have understood the entropy of a black hole, but what we have not understood. Okay, so we got the entropy to work out. These are extremal black holes. They have mass equal to charge. Such black holes don't actually radiate. So it's a property of gravity that if mass is equal to charge, it can't radiate. And there was nothing to radiate here because if you just had, gravity was running around the circle, they just keep running around. There's nothing they can do. They just keep racing around the circle. But now suppose you had gravity was going both ways on the string. That's more interesting because suppose you had a string, a normal guitar string, let's say wrapped around a circle like this, and you send a wave going in one way. Then the wave will just keep racing around. But suppose you have waves going both ways, standing waves going this way and that way. Those are the guys that actually interact and they come off away from the string. The energy can be lost from the string and comes off as sound waves. So when you have a guitar string which is plucked, you have both left and right movers, and that's what couples to a sound wave because sound wave is coming like this. It doesn't have any momentum this way or that way. So the momentum cancels, the energy adds, it goes off the string becomes quiet, and the energy comes to you. Right? So that's how black holes radiate. So now what we really want to get to slowly is black hole radiation because we want to compare to Hawking radiation, information, all that story. So extremal black holes are okay because they got us the entropy, but it's not all that we need. We actually want to get things which radiate. So how do we get that? We're going to look at near extremal black holes, which are not really extremal. What we're going to do, the simple way to do that is to have some momentum modes going this way, but some guys also going the other way. See, everything is so simple. What else could you have? So you just do that. So if we call these D1 brains, we call these D5 brains. These guys are carrying momentum, we call them P. If they carry momentum the other side, we call them P bar, because like anti-P. Is that okay? Just notation. So D1, D5, P bar black hole, this is the picture at weak coupling. And so you can compute the entropy of this, because now you have some ways of partitioning this momentum, you also have many ways of partitioning this momentum, and you can count how much entropy you get. It turns out the entropy is 2 pi root N1, N5, number of 1 brains and 5 brains, number of P guys you put, number of P bar guys you put, it somehow comes out like this. Okay, go back to the gravity, make a black hole which carries this much of P and P bar charge and everything, put all the charges in, find the area, and you find again matches beautifully with the area by 4. Okay, so even non-extremal black holes are working beautifully, and but now we are in a good situation. If the entropy is working for this, we sort of understand this guy. But if this guy and this guy collide and they come out, we can compute the radiation rate. At what rate are they radiating? And if that matches with the Hawking radiation rate, then okay, then we are understanding even more about black holes, right? So you can compute radiation from near extremal holes. And so we are going to take this and this, they're going to collide. So we have lost, let's say, some of them, some of the energy has come off, and you can see a radiated graviton. Okay, this story. So I'm out of time today. So when we have our next lecture, we will pick up from this point, start with the computing the radiation, see where Hawking radiation is. We will actually still have the puzzle because our picture of the classical black hole is still this picture. And that doesn't help us because then we have information loss and all the pair creation, entanglement, all these problems. But then we'll actually have to compute the structure of these same states we made at weak coupling. We are going to find these states at strong coupling. So that's the whole fuzzball game. Can we really find these states at strong coupling? At first people thought at strong coupling we can't compute anything, let's just compute them at weak coupling. But turns out you can also actually find many of these states at strong coupling. And when we do that, we'll actually explicitly construct them using language as simple as this language, but we'll find they never have a horizon. So the traditional picture of a horizon was not correct. We'll find in all the cases where you can actually make the state, there is never any horizon. Okay? And so that will actually come, that will be a strong coupling, so now we really have the black hole, and then if we don't have the horizon, then we don't have a problem. Right? So then that's what we save for our next lecture. Okay, thank you. Are there any more questions for me?
No, next lecture is, I should make an announcement. The next lecture is at 4 o'clock on
Thursday.
18th is Thursday. So, because there are some clashes and so on. So 4 p.m. So same place. No, I think I'll announce it, but 4 p.m. on Thursday. No, not 2:30. That's what mine.
Yeah, question.
So you said that extremal black holes do not radiate.
Yeah.
So then what happens to the earlier using Hawking argument that said that because of pair production, any kind of black hole should radiate, right? So what happens to that?
Yeah. So what happens is that if they also have charge, you have to think again. Because if you have charge and then you create a pair of particles, then there's also an extra energy from the charge interacting with the field of the thing, right? We included rest energy mc square and gravitational energy, gmm over r, minus gmm over r. But it's also a q1, q2 over r kind of energy, right? When you take that into account, you find the extremal hole doesn't actually have that negative energy states in there. So if you have too much charge, which is charge equal to mass, then they will not radiate. For the extremal hole? Yeah, but that is the horizon. They do become one, the inner outer horizon meet, but in some sense.
But the metric doesn't change sign because we immediately go into the right sign.
Yeah, so it's a very different black hole. And so, yeah, if the metric had changed sign, you had a smooth horizon, it would have to radiate because the argument we gave was so simple, right? If you have a horizon, if light cones here go this way, here go this way, you will always have radiation. So this external black hole doesn't have that kind of horizon. And exactly, you're right. Therefore, it doesn't radiate. That's all true. So that has always been an issue. Nobody has been able to prove in very, very conclusive way that for near extremal, all these arguments that weak coupling should be equal to strong coupling because supersymmetry, they are not exact anymore because the state is not really supersymmetric. So, but remarkably, many of the things work out exactly. Like this entropy thing, for the near extremal, the fact it works out exactly is just an observation. But people tried to make it more accurate by some logic, but nobody has really succeeded.
So there is no non-denominator. There is also, I think, a paper by Strominger, Horowitz, and Marmosena, which has all of them.
Yes. So it continues to work even all the way for neutral black holes. If you just keep using this kind of formula, it works much more beautifully than you would ever have expected. Even for the short shell black hole, if you had NP and NP bar, N5 and N5 bar, N1 and N1 bar, you can make a neutral black hole which has no net charge, and the formula still works down to the last factor of 2n pi. So nobody has understood that.
Nothing is known.
Nothing is known. If everybody could prove why it works, it would be beautiful. But nobody has understood why it works so well. Just magic.
Because there is a ADS3, there is left and right excitations in the CHEP. And so if you use ADS3.
So with ADS3, you can get this far probably, right? But you can't understand why it also works with root N1 plus N1 bar, root N5, okay, why it works even for short shell. That's the magic.
So these are not supersymmetric. Because no, ADS3 is, but I'm saying that once you have away from extremality.
They're not supersymmetric.
That's why ADS3 you turn on left and right excitations.
They're not supersymmetric.
But will it have an interpretation in terms of the original non-extremal black hole? It's not
That's somehow the near horizon.
That seems a little.
Yeah, once you start getting N5 bar and N1 bar, it's not in ADS anymore, right? Yeah, it's not ADS. This one, you're absolutely right. You can put it in ADS and try to make sense.
So this is basically all the left-moving and right-moving excitations together will count the thing for you, even though you do not really understand the original black hole is not supersymmetric. That's the claim.
Yeah, that's the claim. That's the surprising thing. Yeah.
This teacher runs to mean, this twist, the
Yeah.
twist operator, what does it look in this picture? This splitting and joining strings. I mean, you don't have an independent thing for that.
Okay, so,
The Z2 twist operator, it joins the strings
Yeah.
and so on. So in this picture, how does
so it's not
the
Z2.
product is clear.
If you take the sigma k twist operator which joins k strings, right? So the sigma k will join k of them and create this, and that's the chiral primary.
Yeah, that is something you have to put in. I mean, the symmetric product is there. These operators exist.
That's right, yeah.
It exists.
And then you find in the symmetric product theory there are, because it's an orbifold theory, it has twist sector operators. So these are the twist operators of that theory. Of that
Here,
theory.
in this kind of binding picture, I don't see that operator as an operator.
Okay, but you can make but they are the operators and you can show that they are primary operators, right?
Yeah,
And they are
in the
chiral
symmetric product.
in the symmetric product. So then what was the question?
The question is in this picture of fractionation and all, like how do you see that operator?
Okay, so I think I'm not seeing why these are different pictures, because when I was drawing here, to my mind it's the same as a symmetric product.
Only that seems more fundamental.
Symmetric product is there even for K3 and T4, right?
Right.
So then what is the exact problem? I didn't get it.
So, I mean, this is this fractionation and so on, that picture. So, in the symmetric product is, joining and splitting of strings. They are occurred by certain operators.
Yes.
So, in this picture, I'm wondering what that operator is.
Okay, so for me this picture is the same as the picture you're using. They're not two different pictures, because even though it looks like I have many things like separated, that's just a way for me to writing the twisting sector. So in the symmetric product orbifold, there are many ground states, right? Because I have the one which is all singly wound, and then there are, so the general state is sigma k1, sigma k2 up to sigma kl. This is the general state of that ground state of the symmetric orbifold, right? So this is just a pictorial representation of the same thing. So if I look at the guy which is sigma 1, sigma 1, sigma 1, I have drawn it like this. It's just a picture. So the effective string is just a picture where you have n1, n5 copies of something. They are all identical is the only place I need to put in, which is obviously true for strings. And then if they join up, I identify that with this guy. It's just a picture.
So, but for calculations, you have to go back.
Calculations, you can go back here. Absolutely. But the pictures give you everything up to here and the radiation. So it's good for a first pass to do everything this way. Absolutely. It's just a picture. Not added anything.